Welcome to this next lecture on fundamentals of acoustics. In the last class we derived the acoustic wave equation in great detail. I'll continue some thoughts along those lines. Okay. So we ended up with del square p dash is equal to 1 over c square del 2 p dash by del t square. P dash is now the acoustic pressure. Bigger than this you want? Okay. So now we have B, which is rho 0 del P by del rho 0 comma S0. Okay. So this is the adiabatic bulk modulus. Okay. Now what that does is we can write the relation between P dash and rho dash in this form, okay, where B by rho 0 we call it c square, the square of speed of sound. Okay. Now for the ideal gas, the isentropic process is P by P0 is equal to rho by rho 0 to the power gamma. Okay. So from here if we extract P is equal to P0 rho by rho 0 to the power gamma and del P by del rho is equal to P0 gamma rho to the power gamma minus 1 by rho 0 to the power gamma. So del P by del rho I again write as P0 by rho gamma rho by rho 0 to the power gamma. Okay. So del P by del rho, that becomes equal to P by P0, so P0 by rho gamma, and this entity is P by P0, so P by P0 which is gamma P by rho, which is c square. Okay. So now in the equation of state for a constant mass, what we have is P, okay, by rho is equal to RT. Okay. P by rho is equal to RT. Okay. So that P is equal to rho RT, and therefore from here my c square is equal to gamma by rho RT, which is gamma RT, the famous equation C is equal to square root of gamma RT, the speed of sound. Okay. So at say 20 degrees centigrade, which we will consider as room temperature, okay, C turns out to be about 343 meters per second, and we will use 340 in our homework calculations. Okay. Now the next idea is we have this Euler equation which is rho 0 del u dash by del t is equal to minus gradient of p dash. Okay. So if I take the curl of this thing, del cross, if I do rho 0 del u dash by del t is equal to minus the curl of a gradient, and the curl of a gradient is 0. So I have rho 0 del cross del u dash by del t is equal to 0, or rho 0 del by del t of del cross u dash is 0, and therefore u dash must be a gradient of some scalar. Okay. This phi is called the acoustic potential. Acoustic potential. Okay. And now if we do rho 0 del by del t instead of u dash, I put del phi and I have minus del p dash. Then I have del of rho 0 del phi by del t plus p dash equal to 0, and in the absence of sources this is valid everywhere, then what I have is p dash is minus rho 0 del phi by del t. So there is a scalar acoustic potential which is a mathematical construct, acoustic potential from which if you take the gradient you get the particle velocity, and if you take the temporal derivative you get the acoustic pressure, and this acoustic potential satisfies the acoustic wave equation. Del square phi is equal to 1 over c square del 2 phi by del t square. So you will find the wave equation written in terms of acoustic potential in many of your papers. Okay. So now we are dealing with this acoustic wave equation. Del square p dash is equal to 1 over c square del 2 p dash del t square. Okay. And this can be driven by initial conditions. It can be driven by boundary conditions, and it can be driven by sources in the medium. Sources in the medium. Okay. As I have said, our focus is harmonic excitation. Harmonic excitation in this course. If there is a harmonic excitation, then there will be transients. The system will go through transients and then follow the excitation frequency. And if there is no damping in the system, then both transient sound and harmonic sound will continue. Harmonic being single frequency excitation. When I mean harmonic, I mean e to the power of j omega t, which we have been seeing. Okay. Now, the thing is that there is always damping. There is always damping in the medium, small or large. Okay. As a result of which the transients will die away. Okay. And the response at the excitation frequency remains. Response at the harmonic frequency, external forcing harmonic frequency remains, continues, which response is called the steady state response. After the transients have died away, steady state response. And these transients die away quickly. So our interest is in harmonic steady state response. Okay. So also we will not consider mostly the initial conditions, okay, because the initial conditions, they generate transients which also die away, which also decay away, let us call it decay away in time. Okay. So now our excitation can be from the boundary condition itself is causing the excitation and a harmonic excitation, or the boundary conditions are homogeneous and we have a source, okay, plus we have a source which is harmonic. So we will be looking at such situations. Transient sound, that means transiently excited. Transient sound or transiently excited sound, which has broadband content, broad frequency content, is useful, but it is very specific, in very specific applications which applies to specific cases. Okay. Like speech, okay, speech is very transient, so if one is studying speech, then you can't ignore it. And situations like bomb blasts, okay, bomb blasts, anything that happens suddenly for a short while. Okay. is useful, but these are very limited in number and very specific cases. However, in most industries, rotating machinery is very common. Rotating machinery, a lot of machinery that we come across has rotating components. So repetition in movement, repetition in vibration, okay, harmonicity in vibration. So harmonic excitation is of importance. Harmonic excitation is important. So that is what we will focus on. And steady state, that means ignore any initial condition effect. Of course, somewhere down the line I will show you how to consider everything, boundary conditions, initial conditions and forcing using integral transforms to solve a problem, but those will be very specific 2-3 lectures. Okay. Now if let's say we have a boundary excitation that is harmonic. Boundary excitation that is harmonic. Okay, then I can say that my P dash is some P of x e to the power j omega t. This is the response. If I substitute it into my wave equation, del 2 P dash del square P dash is equal to 1 over c square del 2 P by del t square. Okay, so let's say I'm just doing one variable, one dimensional x comma t and x comma t. If I substitute this in here, so what I will get is del square plus omega square by c square into P of x equal to 0. The E of j omega t cancels from both sides. Okay, and the double derivative at time brings me omega square. So this is, we know, the wave number k square. So this looks like del square plus k square is P of x equal to 0. This is called the Helmholtz equation. Helmholtz equation. Okay. If this is driven by a boundary harmonic excitation, if there is a force within the medium, then you'll have to put a Q in here, which is of the harmonic nature. Okay, so we will be looking at this sort of problems. Now, what about boundary conditions? Boundary conditions. Initial conditions we are going to ignore. What about boundary conditions? Or rather, what about homogeneous boundary conditions? Okay, homogeneous boundary conditions. Okay, so we said initial conditions we ignore for this course mostly. Then boundary conditions can be homogeneous, in which case we need a forcing, a harmonic force. Okay, so what are these homogeneous boundary conditions? Okay, these homogeneous boundary conditions, because we have, let's say in 1D, let's say in one dimension, the equation looks like del 2 P by del x square is equal to 1 over c square del 2p by del t square. Let me put a dash over here. So now this is where the boundary condition comes from. So you can have a condition where p dash is set to 0 as a homogeneous boundary condition, which is called the pressure release condition. Or we can have del p dash by del x equal to 0, which is the rigid walled condition. Okay. The reason is that the Euler equation in 1D is del p dash by del x is equal to minus rho 0 j omega v dash, particle velocity. So if del p dash del x is set to 0, that means v dash is set to 0 at the boundary, which is no displacement, and therefore we call it the rigid walled condition. So these are the two very common boundary conditions. Now another boundary condition, which is called the Robin boundary condition, is given by del p dash by del n plus alpha p dash equal to 0. Okay. Now if we look at this and our Euler equation, del p dash is equal to minus rho del v dash by del t, okay, Euler equation. For the harmonic case, it becomes minus j omega rho v dash. Okay, this is del p dash. Now if I take a dot product with a particular direction, then I get minus j omega rho v dash dot n. Okay, or now del p dash by del n plus j omega rho b dash dotted with n, okay, equal to 0. Okay, so del p dash by del n plus j omega rho p over z is 0. So this is the acoustic impedance. Okay, and what is acoustic impedance? We typically write it with an A and a complex number, which is pressure divided by velocity dotted with n in a particular direction. Okay, this is my acoustic impedance. So here this is the velocity, this is the pressure, which is the dash. So the ratio of p dash to del p dash del n is being matched with a boundary condition. You know, there is a boundary material. The boundary, there is a material, there is a condition that the acoustic wave sees, and that happens to be neither pressure release, which is soft, nor rigid wall, which is hard. It is in between, and therefore the velocity that happens over there and the pressure that happens over there they have to be related through the wall impedance, acoustic impedance. Okay, this is also called the impedance boundary condition. Impedance boundary condition. Okay, so now if you want to relate it back to the Robin condition, okay, the alpha happens to be j rho 0 omega by z a tilde. Okay, now one thing I will remind you is that the Euler equation is our friend for the harmonic case, because if pressure is of the form a e to the power of j omega t minus kx and velocity is some other b e to the power of j omega t minus kx, then del p del x becomes minus j k into p, that is equal to minus rho 0 j omega del b del t, okay, that is j omega b dash. And so straight away we have a relation between pressure and velocity. No more integrations for the harmonic case. So this equation is going to be of great use to us repeatedly. Okay. So I will close the lecture here and continue. Thank you.